In this problem, we're going to draw the shear and moment diagram of a simply supported beam with a left cantilever. The whole beam is subject to a triangular distributed load as shown here. The maximum value of the load is 2 kips per foot. Okay? Now, you have to keep in mind, right, this is not a uniform load, so this value is just a rate at that point, right? The rate of loading actually changes linearly and goes down to 0 when we get to the left support. So the first thing is to determine the reactions. So first we compute the resultant of the total load, which this is a triangle, so that comes out to be 12 kips, and that's located at 2/3 of the length of the distributed load, because it's a triangle. The centroid is at 2/3, so that comes out to 8 feet. So if we do sum of moments about this support, we obtain 12 times 8 divided by 10 gives us the left reaction, right? So summing moments here, 12 times 8 equals this reaction times 10. So the answer comes out to 9.6 for this, and if we subtract 12 minus 9.6, we get the right reaction, which is 2.4. Okay? Again, it makes sense. There is a lot more load on this side of the beam than on that side of the beam. So intuitively, you should realize, even before solving the problem, that this reaction has to be much larger than that. Okay, we move on to the shear diagram. So to draw the shear diagram, the first thing we need to realize is that this load is, as I mentioned before, it's a rate of loading that varies along the length. So since the rate is going down that way, the slope of the shear is the load, right? So we start with an initial slope of 2, and then that slope goes down. The value of the load right at this point of the support is 1.67, and that's just simply by triangle similarity. That can be obtained very simple. And the rate goes down, and then it goes up by 9.6. This value here of 3.67 is obtained by simply computing the area of this trapezoid right here, right? The total load right at that beginning of the cantilever, that's the shear force, internal shear force. That's going to be 2 plus 1.67 divided by 2, that's the average of the heights, times the width, which is 2, and that comes out to 3.67. Then the shear goes up immediately by 9.6. So 9.6 minus 367 gives you 5.93. And then, again, the slope keeps going down. So the slope of the shear continues to decrease and then eventually gets to here, where it goes up by 2.4. Okay, so the point where the shear becomes 0, it's very important because that's where the bending moment becomes maximum. And to find that, we simply set, this is what we want, that distance, the distance at which the total load applied equals to that reaction. If those two are equal, the internal shear at that point is 0. So we set this equals to x. We set the height of this equals to x over 6, because that's the slope of the distributed load, right? 2 over 12 feet, so that's 1/6. We find the area of that, and we set that equal to 2.4, and we find the value of x equals to 5.36. So almost, not exactly, but almost halfway through here, we get 0 shear. Now, to get the value of the maximum bending moment, positive, and the minimum, negative, we're going to proceed. First of all, since we know the point of 0 shear is here at 536, we simply need to do sum of moments about that point. We make a cut, and we do sum of moments about that point, and we find the positive bending moment, right? To do that, we compute the resultant of the distributed load at that point, right? So at this point here, 536, the value of the rate of loading is 536 divided by 6, so, which is the slope of the distributed load, and that comes out to 0.9. We find the area of this triangle, which comes out to 2.4, as it should be, because those two have to be equal and opposite. Remember, this was the point of 0 shear. So 1/3 of 536 gives you 179. And then you do sum of moments of this force, and that equals to 8.57. And that's the value of the maximum bending moment. The minimum moment right here, we can simply compute it by determining the total bending moment generated by this trapezoid right here. And that we are going to do by breaking up the trapezoid into a triangle and a rectangle, and the resultant of this rectangle here is 167 times 2, and then that's acting halfway at 1 foot, and then this little triangle here, the resultant is the difference between these two, which is 0.33 times 2 divided by 2, so that's 0.33, acting at 2/3, which is 133, and when we sum those moments, we get 3.78, which is the value that we have right here. So stepping back a little bit, we can see the value of the minimum bending moment, maximum bending moment, shear, and all the diagrams here of this problem, which is a simply supported beam with a left cantilever and a triangular distributed load. If you have any questions, please let me know in the comment section.